Okay, so the next paper, sketching vocabulary for crowd motion by Talidu Matthew, Patrick Benesh, and Daniel Aliaga.
So it's my honor to introduce our work, a fusion crowd simulation method, integrating data with dynamics, personalities with common, and I'm the reporter Yan Qingyuan. Well, extensive crowd simulation methods have been proposed these years. They are proposed from different technique points of view to handle this problem. Roughly, they can be categorized into rule-based approaches and data-driven approaches. Rule-based approaches usually generate collision-free crowd motions, but fail to produce diverse motion and natural interactions. Data-driven approaches can generate diverse and natural motion, but fail to deal with collision problem. Furthermore, many data-driven approaches have also high dependency between data and scenario. So the motivation of our work is to take the advantage of these two kinds of methods, and we propose a fusion crowd simulation method to combine both data-driven and rule-based modeling idea. So here is the overview of the proposed model. First, as shown in the left side, the method dynamically models crowd motion using different forces. We assume that the motion of the agent is driven by different forces. Part of the forces are modeled under the universal interaction mechanism, which describes the common parts of crowd dynamation. And others are modeled by example from real data, which describes the personality parts of the agent motion. The forces are determined by the agent state, and this force will update agent state. And what is shown in the right is the example matching part. We propose a construction method for example dataset to obtain understandable and migratable examples from the real data. The comprehensive crowd motion generation workflow is established with the support of this method. And well, now I'm going to introduce the details of the fusion crowd motion model and how it integrates data with dynamics, personality with comments in crowd simulation. First, let's introduce how we deal with the agent moment in our model. Agent moments in our model are regarded in two dimensions, and agents are regarded as disks of radius r with uniform mass distribution. In our proposed model, the agent's position at the next frame is calculated by its position and velocity at the current frame. We use dynamics to model agent velocity change, which is determined by force applied to the agent. As mentioned above, we model forces in agent moment in four aspects: goal-driven force, FD, agent interaction force, FN, obstacle interaction force, FO, and the personalized motion feature force, FP. The first three forces describe the common parts of crowd dynamics, and we set them mainly referring to power law model. This has already been proved to be a fairly form to simulate agent common actions. And the first is the goal-driven force. This force indicates how agents will choose a preferred velocity pointing to their goal if there is no other interference in this sign. Second is the agent interaction force. We apply the special gradient on the interaction energy between agents, referring to power law model. The core idea of the power law model is the interaction energy between agents follows a power law based on agents' projected time to a potential future collision. Thus, the calculate of obstacle interaction force is familiar with the agent interaction force, but the object of collision avoidance is changed from pedestrian to obstacle. The above rule-based model only models the common motion regularities. However, in real agent's moment, personalized factors also play an essential part. So in our model, we use a personalized motion feature force to model these implicit factors like in this downside. And okay. In the proposed method, the personalized force is constructed by a real agent motion example dataset. You can see the component of the example of the dataset in this slide. Every example corresponds to a trajectory piece of a real pedestrian. An example includes its personalized motion features and phase features of a certain length trajectory. Each example is a pair, which means in the given state SS, the real agent has exhibits personalized motion feature as alpha. The personalized motion feature describes the motion characteristic of the given agent, including the goal point, the magnitude of preferred velocity, and the sequence of characteristic differences. The state features describe the states of agents and are used to match the suitable example for generating moments of crowd, including the sequence of positions, the magnitude of initial velocity, and the sequence of density map. Overall speaking, we use the current state of agent to search the most matching state features and use the personalized motion features of that example to get the personalized motion feature force. Next, I will introduce the calculation of personalized motion features. The personalized motion features consist of three parts. The goal point is set as the position of a period after the corresponding segment of agent trajectory, and the magnitude of preferred velocity is the average speed of the trajectory piece. The sequence of characteristic differences consists of the personalized motion feature force FPT at frame t in the example. What is worth mentioned in the calculation of the sequence of the characteristic? In the example dataset construction process, we first use the given trajectory piece and Newton laws of motion to get the resultant force. Then the personalized motion feature force is reversely calculated by subtract the resultant force and the rule-based force mentioned earlier. Next comes the calculation of state features. The sequence of position is the set of position at each frame in the example, and the magnitude of initial velocity is defined as the speed of the frame before the example begins, and then the density map. We abstract agent surrounding state into the density map, as you can see on the right down side, and the sequence of density map represents the surrounding states of the agent at every frame in the example. Every density map consists of L by L grids. The center of the density map is agent position as the first frame, and the grid in the density map has a density that represents distribution of other agents and obstacles. For the density of agents in the grid, we first find all neighbors agents in the density map at the current frame. Then we calculate the relative distance between neighbor agents and the center of the grid. The density of agents in the grid is calculated through the Gaussian distribution of the relative distance. Finally, in the simulation, we match suitable example for agents based on the state features to get personalized motion features. When matching an example in the example dataset, we first predict the future position for such an agent using the linear velocity. After predicting the future position for every agent, we can calculate the state features of the agent, including the magnitude of initial velocity and the sequence of the density map. We calculate the similarity score between the state features of the virtual agent and every example in the dataset. The similarity score is consisted of two parts, as you can see in the slide. The matching example is chosen randomly among several examples with the top similarity score. Furthermore, we use a deviation detection mechanism to rematch a new example to avoid the deviation grow larger as time goes by. The whole simulation process can be summarized in this slide. And next, I will show some experiment results. In quantitative experiments, we use statistics to measure the feature similarity between simulation result and the real data in trajectory and velocity. First, the average perpendicular deviation distance represents the overall shape characteristic of the track. This matrix indicates the ability of our method restoring trajectory motion pattern. And the result indicates that our approach can regenerate the shape of realistic trajectory. The average speed is the average magnitude of the velocity of all agents at average time. As you can see, that our method is a bit lower than the heterosim, but because the heterosim is used the real data as its velocity, but our method can still restore the average speeds even we not using the real speed patterns. And the average speed change is the average change of the magnitude of velocity of all agents at every steps. And then the average angle change is the average of the change of the direction of all agents at every steps. It can be seen that compared to Heathersym and power law, the simulation results of either method are closer to the real data in most scenarios. We also conduct different qualitative experiments to evaluate different approaches further. First, we conduct experiments on generating trajectory. And you can see that our approach established the connection between agents' personalized motion features and state features, thus generating better trajectory based on its surrounding situation. And this experience is to restore the data characteristics. It's designed to visualize the approach ability to extract personalized feature from different datasets. As shown in this slide, our approach performs Heathersyms in the shape of trajectory and the velocity distribution during the agent motion. Thus, to demonstrate that the proposed personalized features has relative low scenario dependency and could transfer to different crowd sense by our fusion model, we conduct the experiment of sign variation. And you can see that our method performs good in different scenarios and can generate collision-free agent motion. So the last we will show a model, we will show a demo about in different scenario. And the left down side input is the real data to construct example dataset, and the right side is a simulation result. You can see that in the 001 dataset, our method can generate a good performance, and you can see that in different scenario that our method can still generate good performance. Yep. And what I want to say is this one, even if the scenario doesn't appear in our construction dataset, we still can restore the motion patterns of the crowd. Yeah, and the final one is a large number of agents entering a narrow passage at the same time. So to conclude, our methods, we propose a novel fusion crowd motion method, and we propose a construction method for example dataset to extract personality features from real data. And that's all. Thank you for listening.
Okay, thank you. I think I need to make a correction. We didn't have, this was not the second paper. Do we have anyone from the second paper here? Okay, so what we heard just now was the third paper, which is a fusion crowd simulation method, integrating data with dynamics, personality, and with common. Which, and the authors was Tianlu Mao, Zhi Wang, Liu Yu Meng, Qingwan Yang, Xiaohao Li, Zhaoqi Wang. I hope I didn't kill those names. Do you have any questions for this paper? Okay, yeah, Panayoti.
Hi, can you hear me well?
Yeah.
Well?
I think maybe you need to repeat it.
Okay, I'll repeat the question.
Oh, yes.
Okay. So I noticed in your quantitative evaluation that the large error was in the university dataset. Could that be because the data are very dense there? So I was wondering if your method is good for very dense crowds or not.
Yeah. The question is if it applies, if the method can be applied to very dense crowds.
Oh, okay. I heard what you mean. Is our method can be used in a dense crowd like this? Yes. So I think that when the crowd became dense, a better way to simulate the situation is use a macro macroscope approaches such as the stream approach and the other approach. Our method is based on the on a single agent, so we use the method. We use this method to commute to simulate this situations is not as effective as macroscope approaches, but I think that our approach still can generate some great results. Yes, so I think the result is yes.
Actually, I have a follow-up question because the university data has a lot of people standing and talking and then dispersing again and stuff like that. Since it's a force-based method, can it be applied to such data where people stand and talk and then stay still for a while and then move on?
Oh, I understand what you mean. In our simulation setting, we just set the initial position and the final position of the agent. So if the agents stand still and talking to each other, we can just set their states as stand still and talking, and not using this method. Yes.
Okay. Okay. Any other questions? I have just one short question. What's the computational, I mean, how computational intensive is it to compute this personalized data?
Oh, you say the computation cost?
Yeah, yeah.
Yes, we use CUDA programming in this program, and I think that it can reach millisecond simulation effectiveness. Yeah.
All right. Thank you very much.
Okay, thank you.